Hi. So I wanted to make a video based on request about splines. And before we jump into the details of splines, let's explain again the motivation behind splines. If we go back to the previous chapter where we did interpolation, what we would do is we'd have a bunch of data points, let's say, and we would draw some interpolant that goes through every single point. Now, something we discuss is that as the number of data points gets larger, and you want to use a higher order of an interpolant, so in this case, we see this is 4 data points. If we have 4 data points, that would mean that we have a third order interpolant. And again, the reason that is that a third order interpolant has the highest exponent of 3. So that would be something like a3x cubed plus a2x squared plus a1x plus a0. We have 4 different unknowns. We use those 4 data points to find those 4 unknowns. We basically create 4 equations from each of the data points. Now, if we have a lot of data points, I'm going to try to draw it as similarly as possible to this, just with more data points in between. Why can't I grab this? Let me move up here. Now, if I try to do an interpolant, let's say it's, how many data points did I draw? 1, 2, 3, 4, 5, 6, 7, which means a 6th order interpolant. We wouldn't see something that's nice and pretty like this necessarily. What we would see instead is something that's maybe a bit more wavy and weird that would occur. I'm exaggerating here. But in general, we wouldn't have our nice interpolant when we had a function of a lower order, like third order or second order. Once we get to 5th, 6th, or 7th order, or something a little bit higher, our function that we assume to go through all the points looks a little bit oscillatory. It oscillates and has this wavy phenomenon, which is bad. So what we would rather do is use splines, where instead of, let's say I'm going to try to copy and paste this. Let's cut this. Let's copy that, paste that. So instead of having one continuous function connecting them all, what we do is we will draw a bunch of continuous functions. I'm going to change the colors of them as we go, that are individually some order, but we connect the dots. Maybe I'll make it black because it's kind of hard to see the green. So what we have here, if we have 7 data points, we have 6 individual splines. This is the first, the second, the third, the fourth, the 5th, and the 6th spline. Because we have 7 data points, we'll have 6 different curves that are connecting them in between. Now, depending on how you want to model those individual mini interpolants, we will determine the order. Maybe we want to do linear splines. If we had linear splines, then in that same picture, which I might still have, I do, cool. Again, I'm going to erase the red. If I did linear splines, what that means is that I will have a perfect line between all of them. I'm trying to make it perfect. That goes in between each group. Now, That's may or may not be good enough. It depends on what you're trying to do. But a big problem of this is that if you were to look, let's say we zoom in here to this point, for example, you have this very abrupt change of slope. If you look at the red line is going with a slope like this, and then suddenly it cuts to, I don't know, not 90 degrees, but it cuts a lot abruptly to go to the black line slope. And we would prefer not to have that. That's not really something physical. So instead what we do is we're going to look at quadratic splines, which is really the big heart of this chapter. So I'll paste this again. Where instead of having all the points connected with lines, we will assume that they are all quadratic functions. They're all second order. Now, the benefit of that is that we can have it where the slope at the connecting points is continuous. So let's go ahead and label these. Let's say that this is f1. This is our function f2. f3, again, we have 6 of them. f4, just to match the colors, I'm skipping. f5 and f6. So at the points where they touch, what we'll say is that the slope of the black function f2 will match the slope of the red function f3 at that point where they touch. So at this specific blue point here, we're going to say that the slope of the black ends up being equal to the slope of the red at that location. And using that fact, that allows us to get the number of equations that we need. So let's go ahead and discuss in general, what equations we would need for splines, specifically quadratic ones. If each function is assumed to be quadratic at first, that means that each function will have, so we'll say a1x squared plus b1x plus c1. That's a quadratic function. We see that there are 3 unknowns for that single curve. So there's 3 unknowns for just this guy, because we're assuming that one section of this entire thing is quadratic in itself. It has 3 unknowns. Now, if we have 6 different sections that are each individually quadratic with their different coefficients, and again, just to kind of write that out further, f3 might be like a3x squared plus b3x plus c3. f2 would be a2x squared, and so on. There's all different coefficients here. We have 3 per spline. We have 3 unknowns per spline. And in this example, we have 6 different quadratic functions. That would mean that we need 18 equations to solve. 6 by 3 is 18. But in general, what we'll say is that we need 3n equations, where n is the number of splines, or the number of curves. So in this example, we have 6 that are each quadratic individually. Each of those quadratic functions has 3 unknowns. If we want to find all of these coefficients, we would need that many equations, 3 by n equations. So where did those equations come from? So we have 3n total. Let me just draw a picture here. Maybe we'll just have four data points. This will be 3 splines. So this will be F1, F2, and F3. And again, I'll just write it out to be really thorough. If you want to fast forward this just a bit, I'm just going to write out what all of these things are, all these functions. We see that we have 9 unknowns. We need 9 equations. So these data points, let's say I call this one x1, y1. Let's call this one x2, y2. This one is x3, y3. And this other one is x4, y4. So if a point is on a function, that means it must satisfy the equation. So if we look at f1, we could say that x1, y1, and x2, y2 satisfy the equation because they are on that curve. If I plug x1 into this function, the output will be y1. If I plug x2 into that function, the output will be y2. So I can plug 2 points into this to give me 2 equations. Now, similarly, let me go ahead and highlight. So these 2 points here are both on F1, therefore they both satisfy the equation. What about F2? Well, what we see is that this point and this point both satisfy the F2 equation because they're both on the spline. So that will give us 2 more equations. And then we have this point and this point that are on F3. That's 2 more equations by plugging into that respective function. So by plugging in points, we get 2n equations. So if I have 3 splines, like I do in this example, I will plug the 2 points that basically create it into the function. That will give me 2 equations per individual spline. So 2 times n will give me the amount of equations. And that will be 2/3 of the way there. We need 3n, we have 2n currently by plugging in points. So maybe what I'll do, let me move this up. So we need 3n total. Oops, that's a little too far up. Maybe I'll say the first, we'll say 2n equations. Those are the first group. The next group of equations comes from the derivatives. So let's look. We need the derivatives to be continuous. Maybe what I'll do, just to have it here so we can write. Our next group of equations, which will end up being n minus 1, this is, assuming equal derivatives or equal slopes. At the junction points, basically where they connect. So if we zoom in, we see here that the slope between f1 and f2 has to be the same at specifically which point? Well, this point. That's where they touch. So an equation we can write is that f1 prime, for this example at x2, has to be the same as f2 prime at that same point. Again, we're looking here at this blue point, x2, y2, the slopes have to be the same there. So if we take the derivative of f1, which again we assume is quadratic, and set that equal to the derivative at f2, which is also quadratic with different coefficients, we can plug in x2 to get another equation. And similarly, you'll do the same thing at x3, except now it's between the two different functions f2 and f3. We see that's where this function and this function touch here. Therefore, we have to set it so that their slopes are equal at the point where they meet. This will give us f2 prime at x3. That has to be the same as f3 prime at x3. And again, just to be thorough, f1 is a1 x squared plus b1 x plus c1. If we take the derivative of that with respect to x, we'll get 2a1 x plus b1. That's a general equation for the derivative. If we plug x2 in, this will be 2a1 x2 plus b1. That will be equal to the derivative of the second function, which will be of the same form, except the only difference is the coefficients. It's not a1 and b1 anymore. It's different coefficients, a2 and b2. So that's how we get an additional set of equations. This will be n minus 1 equations. We can only do it at the point that they touch. If you think about it, we have three different curves, f1, f2, f3. They are touching at two in-between points. That's why we get one less equation compared to the number of splines. We have three splines, we get two equations. So we say that this is n minus 1 equations. So far, we have 2n equations from plugging in points, plus n minus 1 equations by equating derivatives at the connecting points. And we need a certain number now to give us a 3n that we require. We need 3n total to have a fully resolved system. If we add this up, we get 2n plus n is 3n minus 1 plus something has to be 3n. So how many more equations do I need in order to get this to work? I need one more equation, because now if I get one more equation, these will cancel, and that will give me 3n is equal to the 3n that I need. So I need to come up with one more equation in order to resolve my system and get it fully complete. So our final equation is not very satisfying, but between the first and the last spline, so again, I'll paste this again so we can look, meaning between the first and the last, we can have a bunch of splines in between, a bunch of these little baby interpolants in between. But we're just going to look at the first and the last one, and we'll check between first and last spline. We will assume one is linear. So for example, let's say we end up assuming it's f1 that's linear. If f1 is the linear function, what does that mean about our original quadratic? Our original f1 of x, this was a1 x squared plus b1x plus c1. if we assume that f1 is linear, what does that imply about our coefficients? Well, if it's linear, that means that this term doesn't exist, which means that a1 must be 0. And that would be our last equation. The question then begs, which one do you choose to be the linear one, the first or the last? Well, that will be based on the extent that that spline travels. I don't say extent, but the window of x values. So for example, let's say I actually gave some x values. I'll paste this again, except I'm going to change some of these values. Let's erase all this. Let's say that this is at x equals 2, x equals 3, x equals 4, and then this one is at x equals 7. We see that f1 is valid between x equals 2 and x equals 3. Right? That's this guy, f1. It's between x equals 2 and x equals 3. f2 is valid between x equals 3 and x equals 4. And then f3 is valid between x equals 4 and x equals 7. So the one that we choose to be the linear function is the one with the smaller window. So in this example, between the first and the last, this delta x goes between 2 and 3. That means it's going to be a width of 1. That is the extent of this spline, while the other spline has a delta x of 3, which is bigger, which means that f1, this will be the linear one to get our final equation. So once you have all those equations, you would have, in this case, 9 different equations with 3 separate curves. It's 3 of these mini interpolants. We would have 9 equations, 9 unknowns. We can write a matrix where we'd have some matrix. This will be 9 by 9, multiplied by A1, B1, C1, A2, B2, C2, A3, B3, C3. Let's make this a little bit bigger. I'm not going to fill these in. They're in our notes. And that will equal some constants on the right. That will also be 9 by 1. This is our A matrix. This is our X matrix. This is our B matrix. And in MATLAB, we can do that X is equal to A backslash B once we have those matrices filled in. If you'd like me to make a video on actually doing these steps, let me know. But I wanted to go over the concepts of splines, as we've seen a lot of matrix stuff already in the previous chapter. But for now, I hope that this conceptually makes sense with splines. If you have any more questions or any more help, please let me know. Okay, thanks.